Hi everyone. We're going to continue on with our history of the atom in lesson 1B. What I'd like to do is to start by showing you kind of a template that is the pathway that we're going to follow as we go along through the history here. This is actually available up on Schoology, so if you would like a copy of this to fill in as we go through it, feel free to pause the video and download this as a PDF. You may want to print it out. You are not obligated to do that, and you are not going to be turning this in for a grade. So if you'd like to just follow along with the video, that's okay too. So we're going to start off way back in the time of Democritus. So you may have picked up from the Edpuzzle video that one of the first people that ever thought up this idea of an atom as being the smallest particle was a Greek philosopher by the name of Democritus. This is around 460 BC, so roughly 2,500 years ago. This is an incredible kind of step forward when you think about it, because back then they were the first to, or this person was the first to really come up with the idea that everything, large or small, is actually made up of these tiny atomic building blocks. And the word that he used was actually atomos, which is the Greek word for indivisible. So the smallest particles that basically make up everything are these tiny individual sphere-like particles. The next person we actually spent most of lesson 1A talking about, and that was John Dalton. And there's an enormous time bridge between these two. So Dalton's atomic theory this is only about 200 years ago. So this is somewhere around 1810. And remember, he came up with his 5 postulates. If you have not already watched the previous video, the history of the atom lesson 1A, please go back and do that at this point. So this will make a lot more sense, and moving forward will also make a lot more sense. So at this point, in around 1805, 1810, we have what is called the solid sphere model. And at this time, this was the prevailing thought about what an atom looked like. Again, this is before the discovery of any subatomic particles, so there's no protons, neutrons, electrons, anything like that to speak of at this point. And this model actually dominated probably for almost 90 years. So around 1897 is when we actually take our next step forward. So in 1897, J.J. Thomson is doing some experiments with a cathode ray tube. So I'm going to write that first up here. And just to give you some idea about what a cathode ray tube would look like today, or maybe 20 years ago, if you think back to before flat screens, you might have to ask your parents about this. We used to have television sets that were about 2.5 to 3 feet wide. Now, I don't mean left side of the screen to right side of the screen. I mean front of the screen to the back of the television set. And the reason it was so wide is because in there was a giant kind of glass tube, a cathode ray, that was actually used to create the image that we saw on the front of the screen. That's similar to what was going on here. So a power source is hooked up to this discharge tube here, and we get this stream of particles. He originally called them corpuscles, but they eventually became what we know today as electrons. So this stream of electrons, they were able to use magnets to bend the stream, and they were able to identify the charge and the mass on an electron. We'll talk about that later. But that actually created, or led to the creation of, our next model, which is the plum pudding model. And again, this is all around 1890 97 or so. So about 87 years after Dalton's atomic theory came out. So the plum pudding model had electrons here embedded in a positively charged mass. So at this point, they were aware that the charge on an atom was neutral, so there weren't any charges shooting off of it. So it had to be a neutral charge, and we could account for the electrons, but we really couldn't account for what was the positive part of that, why it was neutral. So they just assumed that the rest of the matter that was present in an atom had to be this like kind of positively charged jello that these electrons were embedded in. The term plum pudding is not something that we're really familiar with because many of us have never seen or eaten plum pudding, but I like to think of it almost like a chocolate chip. So if you imagine a chocolate chip where the chocolate chips are the electrons and the rest of the cookie is that positively charged matter. Of course, it would be in 3 dimensions. So this was the prevailing thought, but this actually only lasted a short period of time. So what you're going to notice is that new scientific discoveries start taking place a lot faster. So if you notice, there was thousands of years going from Democritus's original idea, and there were other ideas in between, but the major prevailing change came with Dalton in 1805 and 1810. And now 90 years later, and now we're going to go to just about 15 years after this, where we start talking about the next model. Okay, so our next model starts off with the Rutherford gold foil experiment. So the Rutherford gold foil experiment led to the discovery of the proton. This is taking place around 1911, so only about 109 years ago. So if we look at the Rutherford gold foil experiment, we have a source of radiation. So in this case, it's shooting off alpha particles. And those alpha particles are directed at a piece of gold foil. And then behind this gold foil is kind of a phosphorescent screen that will show just a little burst of light every time one of these alpha particles hits it. And what Rutherford noticed was that the overwhelming majority of these positively charged alpha particles went straight through the gold foil and did not hit anything. But every once in a while, one of these positive charges hit something, and you knew that it hit something because its trajectory was changed. So this might have gone through and been deflected, and been deflected down like this, or it might have gone through, hit something and bounced back. So the original pathway had almost all of them hitting right back here. Now, every once in a while, he started to notice that one of these alpha particles' trajectory was changed. And he concluded that there must be a dense positive charge in the center of this atom. So we're going to put here discovery of the proton. As the dense positively charged center, which we now know is the nucleus. And that term led to our nuclear model. And in the nuclear model, again, this is around 1911. In the nuclear model, we still have our Thomson electrons. Now we have a nucleus where the protons are located, and that is positively charged. Notice that the electrons are still kind of just scattered about the atom. It wasn't until 2 years later, in about 1913, that research done by Niels Bohr led to the idea of energy levels. Again, this is around 1913. And in the Bohr experiments, basically what they were doing was they were firing energy into an atom, and they started to notice that when the electrons were excited, they moved to a certain level, and when they fell back down, they gave energy off, they released energy of certain wavelengths. And based on the different colors of light that emerged, they were able to conclude that electrons aren't just randomly floating around in an atom. In fact, they are confined to these very specific discrete energy levels. So the idea of energy levels and electrons being confined to these energy levels came around 1913. That led to our next model. So as you can see over here, over my shoulder, our next model looks like a solar system, very much like something you might have created in 2nd or 3rd grade. And for that reason, it became known as the solar system model or the planetary model. So clearly in this model, which again was around 1913, we can see our electrons are confined to specific energy levels. And we still have our protons in the nucleus. So all of these different ideas are building on one another. No one's really being refuted, it's just the ideas are being refined. So the idea of a positively charged nucleus still exists today. And our electrons being in energy levels, again, that idea still exists, even though it looks a little bit different than our planetary model. So for the next part, and I'm going to go over 3 different scientists at this point, for our next part, we have 3 different discoveries. So around 1927, we have the Heisenberg uncertainty principle. And what Heisenberg said was that the more precisely you know the location of an electron, the less precisely you can measure its momentum. And if you think about it, this is how I like to think about it. If you imagine that you're watching a horse race and you take a snapshot of a horse running along the track. So based on the picture that you take, you know the exact position of that horse at that time, whatever time stamp is on your picture. But looking at the picture alone, you have no idea of how fast that horse is running. On the other hand, instead of looking at one brief period of time, one instantaneous period of time, if you measured the distance that a horse ran from start to finish, you could calculate its velocity and therefore its momentum. But at no time during that entire time frame would you know its exact position unless you took a still shot, at which point you lose the ability to track how fast it's going. So Heisenberg said, this can't be. We can't have electrons that are on these predetermined pathways. So instead, he thought, along with Schrödinger, so we're going to add in here around 1932, that electrons were in energy levels, but the energy levels were not just these concentric circles. So instead, they came up with this electron cloud model. Around the same time, so sometime around 1930, we also had a scientist by the name of Chadwick discover the neutron. So they started to look at their calculation of mass, and they realized that they were not accounting for the mass, because when they knocked off an electron or an electron was absorbed, the mass didn't change significantly. So if initially the thought was, okay, well, protons have a mass of 1 atomic mass unit and electrons have a mass of 1 atomic mass unit, then losing or gaining electrons should change the mass, but it wasn't. So they figured out that there must be some other particle about the same mass as a proton, but with no charge. And that's where the idea of a neutron came to be. Okay, so that was just a brief history. Again, if you would like more in-depth, please go ahead and read through the chapter on atomic theory in your textbook, or search atomic theory on YouTube, and you'll find countless videos that go into a lot more depth. What we're going to do next is we're going to try this activity that I've developed. It's kind of a cut and paste activity that I've modified for virtual learning. So I'm going to show you what the activity looks like on the next page. Okay, if you look at the screen here, you'll see the activity is basically composed of two parts. They're on the same document. So when you open up the document, you're going to see this kind of colorful data table-like thing. And on the second page, you'll see a whole list of scientists, dates, pictures of what the atom looked like, and some explanations. So you're going to take these pictures, statements, scientists, and you're going to drag them into their appropriate spot. Now, if I could give you a few recommendations, the first recommendation would be to please go ahead and put the dates in order. So top to bottom, put the dates in order. That's really going to help you. Then, if you go back, if you wrote down stuff during this video, that's going to be really helpful. If you didn't, you can go back and play parts of the video to try and get a sense of where other things go. Now, if you look back at the columns, so we'll just slide back here for a second. We have the dates, that should be your first column. The scientists, now for the most part, there'll be one scientist per box, but I'm telling you now, there will be 3 scientists in this bottom box here. Next thing is, you'll notice that there are 5 different pictures of the atoms, so those can go into these 5 boxes. The nickname for the model, so if you notice, there are nicknames for the models on the side, like the electron cloud model and the planetary model. And then finally, in the last part, we're going to put in there the evidence, the research, the experiments that led to that model. Here's where it's kind of tricky. I'm going to give you a piece, an answer right here. So this first line right here is going to be Dalton. Dalton, remember, had 5 postulates. So this box here is going to have 5 different things in it. You'll notice that it's not going to be even all the way down. This one has 5, this one has 1, this one has 1. So you cannot just kind of divide them up evenly and just place them in. So 5 postulates, they're up here from Dalton. Please make sure all 5 postulates end up in the first box. After that, you can go through and assign the different experiments to their individual boxes, of course, lining them up with the appropriate scientist's date and model. If you have questions as you go through this, please feel free to reach out. The other thing is I want to mention, sometimes as you're moving them, it appears that the object you're moving has disappeared from the page. I assure you it has not. So it has either ended up at the top of the page or down at the bottom of the page or even on the next page, but it didn't disappear. So if you are dragging something and you lose it, you'll find it. It's there. You just have to move the page around in order to see where it went. Okay, I hope everyone has, I think, a fun time doing this. And if you have any questions, again, please feel free to reach out, and I'll see you for our next lesson. Bye, everyone.